Hi everyone, welcome back from lunch. I hope you managed to have a bit of a break after our system dynamics session this morning. I hope I think I've probably put quite a few people off system dynamics, which wasn't my intention, but hopefully you can see why it's not necessarily always the best solution. In fact, I saw quite a few people in the groups who I thought, do you know what, this would work better as a discrete event simulation, and that's quite common. That happens quite a lot. But I did see some really interesting stuff, nevertheless. So if you haven't already posted the link to your model, please do so. Sammy and I have been looking over them, so please make sure you share it if you want to be counted there. Share that in your PSG channel. As I said, I'm not the greatest fan of system dynamics. If that is now you, you never have to hear about it again. I will say it's probably worth doing alone just for the experience of going around the groups, having started by two groups actually in a row who were looking at a nice sort of bakery model, really nice. Then I went into a room where they were stockpiling bodies of antelopes, and then another room where they were had a slider for the number of chainsaws to decapitate zombies. So, you know, we really had the full spectrum of ideas there. So fantastic, really creative stuff that you came up with, and hopefully it's given you a bit of a chance to have a play around with Insight Maker and see what it can do. But this afternoon we're going to start talking about some proper modelling, and we're going to talk about agent-based simulation, which is kind of similar in vein, I guess, to system dynamics. In the it's trying to capture something a little bit more nebulous in terms of the system, but I think probably a slightly more robust approach. Agent-based simulation is what my background's in. I did my PhD in agent-based simulation. I'll talk a bit more about that in a bit. And I'm a great fan of agent-based simulation. We have never had we had one HSMA project that tried to do an agent-based simulation last year. Unfortunately, the guy had to drop out. But we have never had a proper agent-based simulation HSMA project. So I'm throwing down the gauntlet because I'd love to see one. And I'd be interested to see what people could come up with on this. So let's talk a bit about agent-based simulation now. And really, agent-based simulation is all about trying to capture the behavioural aspects of a system. So when we've looked at things like discrete event simulation, that's kind of focused on the processes within a system. It says, you know, you come in and this thing happens to you, and then one of these things happens to you, and then something else happens. And so you're starting with the kind of processes of the system. But actually, sometimes there are behavioural aspects. I mean, there are behavioural aspects in most systems, but they're not always important. So, you know, a lot of discrete event simulations, you're focused on the pathway, really. But sometimes those behavioural aspects are important to your system, and therefore your question what you're trying to model. So this afternoon and next week, we're going to be looking at how we can model those kind of behavioural aspects using agent-based simulation, or commonly referred to as ABS. And agent-based simulation is all about emergent dynamics, which we'll talk a bit more about in a moment. And to try and understand what we mean by emergent dynamics, and to give you a sense about how this is a kind of slightly different, again, way of modelling, we're going to first look at something called cellular automata, which is basically a type of mathematical model that is kind of the purest imaginable agent-based simulation. Now, we used to have this as a separate session. I've changed that now. I'm not expecting anyone to probably go, I mean, you might, but it is unlikely that you'll go off and think, I'm going to build a cellular automaton model. But hopefully the principles that I show you here will help you understand the kind of thinking that you want for an agent-based simulation and the kind of thing that you're interested in when you try to model your system in an agent-based way. So let's talk about cellular automata a little bit first. So what are the core components of cellular automata models? They basically have an n-dimensional grid of cells, so they can be any dimensions. Most tend to be either 1 or 2-dimensional. The top picture here is actually an example of a 1-dimensional cellular automaton. It's actually going through various stages, but it's actually just a single line is one generation, one sort of time step, if you like, in its evolution. And this one down here is an example of a 2-dimensional cellular automaton. And basically, the cellular automaton, each cell is in one of a number of different states, and time advances in these time steps that we call generations. And the state of those cells may change across the generations according to what are usually very simple rules. And the rules that determine the state of a cell in any given generation usually draw on the state of a cell in a previous generation, so what it was before, and or the states of the cells in its basically around that cell, which we refer to as the neighbourhood. So basically you've got an n-dimensional grid of cells, usually 1 or 2-dimensional. Each cell's in one of a number of different states. Time advances through generations, and those states of each cell basically updates according to simple rules, and those rules generally are things that draw in what state it is in now and what state the neighbouring cells are in. So in the natural world, there's actually lots and lots of things that we can't explain using conventional mathematics. So really famous examples, the formation of a snowflake or the patterns on a seashell. These things can't be explained using conventional mathematics, but can be explained using cellular automata mathematics. And we also find examples of things that that can be captured well by cellular automata within human systems too. So the way in which traffic jams form can be modelled and has been modelled using cellular automata. The idea that there are essentially individual vehicles that are each making very simple decisions, but that can have a knock-on consequence for the population as a whole, for the traffic flowing through. And the crucial thing about this is that these phenomena that we're talking about typically arise emergently. So you have this idea that you have very, very simple rules, usually incredibly simple, that are then kind of consistently applied at an individual level, and then that leads to emergent behaviours, emergent dynamics that actually appear much, much more complicated. So very simple rules. I think the study years ago that used cellular automata to look at traffic jam, you can get a traffic jam. Sometimes, when you see a line of traffic, you think, well, I don't understand why is there a traffic jam? There's been no accident or anything like that. And it's just that somebody chose to move into the overtaking lane at a certain point, and that had a knock-on consequence and led to this more complex behaviour happening at a population level just through that very simple individual level decision. Now, you may have heard of possibly of one of the most famous cellular automata, and that is John Conway's Game of Life, sometimes just known as Life, and was devised by John Conway, who was a mathematician. And basically, Life is an example of a 2D cellular automaton, so it takes place on a 2-dimensional grid of cells. And each cell can be in one of 2 states, which represent being alive or being dead. And it uses something known as a Moore neighbourhood, which basically says the neighbourhood of any cell is itself plus the 8 cells that surround it on a 2-dimensional grid. Okay, so basically north, south, east, and west plus north, east, south, west, etc., etc. Now, the game of life actually just consists of 4 very, very simple rules. Rule number 1, if you've got a cell that's alive and it has fewer than 2 neighbours who are alive, so 2 of the cells in the 8 cells around it are alive, fewer than 2 of those, the cell will die in the next generation, and that emulates underpopulation. If the cell is alive and it's got either 2 or 3 alive neighbours, then the cell will live on in the next generation, so it'll continue to live. If the cell's alive and it has more than 3 alive neighbours, then the cell will die in the next generation, this time through overpopulation. So basically, if the cell, if it's alive, it needs either 2 or 3 neighbours. Any less than that, and it will die. Any more than that, and it will die. And then the 4th rule says if the cell is currently dead, but it has exactly 3 alive neighbours, then the cell will be born, become alive in the next generation, and that emulates reproduction. Okay, so if it's alive, it needs 2 or 3 neighbours to remain alive in the next generation. If it's dead, but it's got exactly 3 neighbours, then it will become alive in the next generation. So really, really simple rules. That's all this is. 4 simple rules in a cell where in a grid where each cell is either alive or dead. That's all it is. That is the entire game of life in its entirety. So 4 really simple rules, but what's fascinating about the game of life and many cellular automata is that out of these really, really simple rules, we get incredibly complex behaviour emerging. And in particular, we get these things known as patterns or life forms that have actually been found to emerge when you play the game of life. And these patterns tend to fall into different categories. The 3 main ones are things called still lifes. So these are basically patterns that don't change from one generation to the next, they just remain static. And then you've got things called oscillators. And these are basically patterns that repeat after a certain number of generations, and that period is known as the period of the pattern, so the time, the number of generations for it to repeat. And then there's these things called spaceships, which are basically patterns that tend to move themselves across the grid. Again, I emphasise to you 4 simple rules, 2 states. That's all that it is. And yet we're out of this generating life forms of many different kinds. So before we have a look at these patterns in more detail, let's actually have a look at life in action and see what we can spot. So first of all, we're going to go to this link here. You'll have a chance to play around with this in the exercise 2. So it starts you off with this pattern here. This is actually known as a glider. And you'll see why. If I click start, this is just going to apply, it will go through in time steps, in generations, applying those rules that if a cell is alive, as long as it's got 2 or 3 neighbours, it'll remain alive, otherwise it'll die. And if it's dead, as long as it's got exactly 3 neighbours, it'll become alive. So let's click start and see what happens. And we notice this life form seems to be moving throughout our world. We in no way created that behaviour. We just set up some really, really simple cellular rules. And in fact, there's all sorts of interesting things. You can actually play around with this. You can draw your own. Let me just draw something random, see what happens, see if we get anything generated. I have no idea if this will work or not. Let's just see what happens. Let's click start and see what appears, and I bet we'll get some life forms. Yeah, we did. And so this here, that's known as a still life. We saw an oscillator a moment ago as well. I think we're going to get another one born in a second. But you can see these little life forms. That one's now been consumed. Now we've got another still life that's been born down here, and another one here that's just been consumed. And we've had a glider up there. We've got more still lifes that have been born. This again, 4 very simple rules that came out of this. In fact, you can explore some common life forms if you click on the lexicon. There's different ones that you can select. Let me just go to, Just one bit. Where is it? That one here. Let's go to this. Let's see an example of a spaceship. Let's click start, and we see this life form here, which you may recognise from the title credits in the video, is gradually making its way across our world. We've created that, and yet it has just been born out of these incredibly simple rules. 4 simple rules have created what appears to be very complex emergent behaviour. Just also going to show you this link as well. There's lots of different links you can look at online for the game of life, but this is quite a nice one here. So this allows you to play some different patterns here as well. You can set it up by default. It's toroidal, which means when it goes off the end, it'll sort of wrap around, a bit like Pac-Man, basically. And we can see here, this is fascinating. Again, game like this is incredibly simple rules here that are being placed exactly as those same 4 rules. Look what's happening. This you would not, if I just shown you that, you would not assume those 4 simple rules had created that. And again, we see all sorts of interesting stuff. We can click difference here. There's sort of gun type formations where it's firing off these kind of missiles here. The Trans Queen Bee shuttle. Amazing, astonishing behaviour. And now hopefully you can see a little bit of why when we said about things like snowflakes can't be explained by conventional mathematics, but can be explained by cellular automata. This is kind of what we're talking about, that we're seeing this more complex behaviour emerging out of this stuff. Okay, so we talked about these sort of 3 main types. So let's talk a little bit more about them because it isn't just random things that are coming up. It turns out that there are common shapes that are common life forms that appear time and time again. So let's look at still lifes first. So as I said, still life is basically a pattern that doesn't change from one generation to the next. In fact, I think, well, we definitely saw 2 of these. I think we may have even briefly seen a loaf in there as well. And we definitely saw the block. We saw the beehive pattern appear. And as I think we saw the loaf. And if you take a moment to think about it, it makes sense why these are still lives. If we break it down, we know the rules of life. In our automaton here, each of those cells, well, that one's got exactly 3 neighbours, so it'll live. That one's got exactly 3 neighbours, as is that one, as is that one. But no other cell can be born because no other cell has exactly that is dead has exactly 3 neighbours. So we get that still life pattern here. And the same, if you have a look at these ones, you can see if you apply those rules, you can see why they don't change. Then we've got these things called oscillators. So oscillators are the ones that basically patterns that repeat after a certain number of generations or the period. And a couple of common ones that you will see. Again, we saw an example of a blinker, although you did have to sort of blink and you miss it, but it did appear when we looked at it a moment ago. So this is one that life form that moves between this shape and just keeps oscillating between the 2. So this has a period of 2. Because it repeats after 2 generations, so 1, 2, it's back to where it started. And this shape here is known as a pulsar. This has a period of 3, so it moves from this shape to this one, and then back to this. Again, fascinating things that have emerged time and time again when you play life. Then we've got spaceships. So spaceships being patterns that move across the grid themselves, and they also repeat after a certain period, but basically in a different location. So they're a good way to think of them as a bit like an oscillator that kind of moves. And the most common spaceship you'll see, as indeed we saw multiple times in those examples, is a glider that gradually goes through these shapes and then sort of gradually moves itself across here. And so what's the period of this spaceship? Well, if we have a look, 1, 2, 3, 4 is where it starts repeating, so this has a period of 4. We've also got these things called eaters that emerge in the game of life as well. So eaters are fascinating. Eaters are basically an example of a still life that can interact with other patterns without suffering damage to itself. And it basically appears that the eater consumes the other life form whilst retaining its own integrity. And if, by the way, if all this is starting to sound familiar, cast your minds back to the very first session of HSMA that we had, our welcome to HSMA induction session, where I asked you to present what you thought this slide meant about spaceships and eaters consuming and all that kind of stuff. Now you know, and I did say one of the groups actually got some of the way there, which was impressive. So let's have a look at an example of an eater, because why not? So here, this is an eater here, and up here, this is a glider, a spaceship that is coming in. This spaceship is going to be eaten by this shape. Let's watch it happen. It's gliding in. You can see it's a still life. The eater is a still life. It's consuming the spaceship, and then watch as it goes exactly back to how it was at the start. This is known as an eater. Again, I put to you 4 very, very simple rules have led to this emergent behaviour occurring. And actually there are a lot of patterns. There are patterns that continue to be discovered even now. There's actually an annual contest called the Pattern of the Year contest, in which people submit basically interesting stuff, interesting life forms they found, and they get judged. I don't know if they win anything, maybe they do, I don't know. But you can actually have a look at some of the previous entries here. There's some fascinating stuff. So, if, you know, it's really interesting. It's certainly an interesting area, I think. However, I'm sure you're probably sat there thinking, well, yes, it is interesting. It all sounds fascinating. But why should we care about any of this? What's this got to do with us? Why is it so important that this thing creates these patterns? Well, basically, the fact that these patterns, these life forms, emerge from the game of life, demonstrate that from simple rules, we can have emergent self-organizing behaviour at a population level, just from those simple rules at an individual level. And that is a fundamental principle of agent-based simulation. That you have simple rules that individuals are acting on, but actually that causes really interesting complex dynamics at a population level. And it also shows us how order can emerge from what appears to be chaos. Okay, any questions so far, Sammy?
No, I don't believe there have been.
Awesome. Okay, so before we move into agent-based simulation itself, I thought it might be nice just to take a short pause just to give you a chance to have a play around. What I think we'll do, we'll just keep it to about 20 minutes, and probably, unless, I mean, feel free to take a break, but obviously we're running a little ahead, so, but I want to give you more time for the final task. I think would be more useful. So I'm going to give you about 20 minutes. So we'll come back just after quarter past 2. I want you to go into your groups and have a play around with the game of life using these links. See if you can get what patterns you can get to emerge. Explore the lexicon stuff. You can play around with a one-dimensional elementary cellular automaton simulator here. One-dimensional elementary cellular automata are really interesting. I'd definitely encourage you to have a look at that. Also have a look at this thing called the Edge of Chaos, which is something that appears from a one-dimensional elementary cellular automaton. This is fascinating, the whole Edge of Chaos thing, and it creates some really pretty stuff. So do check that out. And you can also have a look at some other 2D cellular automata as well. There's one called Star Wars, and you'll see why when you run it. There's one called Brian's Brain. There's a full-on simulator here. So I'll give you till 20 past, so just over 20 minutes. Go into your groups now. Just have a little play around with this and just see what you can explore, and just immerse yourself in this world for a moment before we come back to talk about agent-based simulation proper. Okay, let me stop sharing. Hi everyone, welcome back. So hopefully you had a bit of a chance to play around with the game of life and some other cellular automata, and probably noticed that there's an entire world, a whole new world out there of stuff, of life forms being discovered, and nomenclature that you could absolutely absorb yourselves into if you so chose to. But the key thing I wanted to really emphasize from all this was this idea of very complex seeming emergent behavior, as effectively simple life forms that seem to be emerging out of very, very simple behavioral rules. And that's going to underpin really what we're going to be talking about in the agent-based simulation. So let's move on back to the slides. Let's now talk about agent-based simulation properly. So agent-based simulation, or ABS, basically it's a simulation approach that tries to focus on behaviors within a system, interactions between actors within a system, and the motivations of individuals within a system. And just as with cellular automata, you're trying to observe basically the emergent behavior, the stuff that emerges at a population level from these individual level behaviors, these individual level interactions, which are often pretty simple rules. Now, agent-based simulation is very, very commonly used in ecological modelling, and I'll talk a bit more about that in a moment. That's what my PhD was in. Typically in ecological modelling, it's known as individual-based modelling, or IBM. So if you see that term, it's the same thing. They're both referred to agent-based simulation. And it's called that basically because we tend to know in ecology, we tend to know much more about, or can make many more assumptions about this, the behaviour of an individual animal than we can about population level dynamics. And so that's why it's so commonly used in ecology. And of course, also very commonly used, as we mentioned earlier, of course, in computer games. If you've played any of these and more here pictured, which I'm sure at least some of you have. I know there's a lot of Roller Coaster Tycoon fans from earlier in the course that flagged this up. You have played an agent-based simulation. These are all examples of agent-based simulations. Probably the Sims being one of the most famous and long-running. Is a perfect example of what an agent-based simulation is. That you have individual agents, in this case your Sims, who are interacting and have their own sort of behaviours and motivations and interactions within an environment. And in fact, there's a little video here which describes how the agent-based simulation aspect of SimCity works. So you can check that out if you're interested. But if you want to know what agent-based simulation is, if you've ever played any of these things, then you have essentially interacted with an agent-based simulation. Now, there's basically two key aspects to an agent-based simulation. You have an environment, and basically the environment is the kind of the world in which your agents live. What that world represents will differ depending on what it is that you're trying to model. So, the world, the environment is in SimCity would be your city. In Theme Hospital, it's a hospital. In The Sims, it's originally it was a house, but now it's a whole sort of neighbourhood. A theme park, if you're playing Theme Park or Roller Coaster Tycoon, those are the environments in which your agents live, and they also contain things that are not agents with which your agent can interact. And then, as well as the environment, you've got the agents themselves, and the agents are basically your sort of individual actors within a system, and each agent will have its own behaviours, its own needs, its own motivations. They can interact with each other, they can interact with the environment in which they live. Very often, agents are kind of living beings, whether that be people or animals, if you're doing ecological modelling. But it's important to stress that they do not have to be. So you can have agents that are not living beings, as long as the things that you are modelling as agents have behaviours and interactions. So you can have organisations, for example, that are represented as agents in your model, as long as they have things that that are behaviours and or interactions, then you can capture those as agents in an agent-based simulation. But those really are the two sort of fundamental components of an agent-based simulation. You have agents, and they live in an environment. And beyond that, basically, an agent-based simulation can do pretty much anything you want, and that gives it a lot of flexibility. That flexibility can also make it seem a bit overwhelming as well, particularly if you're newer to coding and or modeling, because something like a discrete event simulation. When I taught you SymPy, there's little quirks and different ways in which you might structure a model, but they all kind of follow the same pattern of, well, you ultimately it comes down to you have things flowing through various activities, and they queue for those activities, and they'll eventually leave the model. Any agent-based simulation will ultimately, any discrete event simulation will ultimately boil down to that. Same with a machine learning model, really, that, if you're building a neural network, well, a neural network is, there's lots of different types, but they're ultimately structured as you feed in some information, some mathematics happens in the middle, and then it spits out a number that you interpret in some way. All of the approaches we've kind of shown you so far have that kind of structure. An agent-based simulation, beyond the fact that you have agents who have behaviours and interactions in an environment, you can do anything you like. So it does free you up a lot more, but there are far fewer sort of hard and fast rules about what an agent-based simulation can and can't be. And that goes back to my point this morning about why I don't like rigid framework solutions for building agent-based simulations, because they can do anything. Now, of course, the other aspect of this is that because they are so free-form, and because you're dealing with behaviours, it can mean that your agent-based simulations are very difficult to parameterize, in other words, to plug in some numbers that make sense, and also to validate, to try and ascertain whether the model is actually completely made up, or is it bears any relation on reality. And these are challenges when you develop agent-based simulations. So I'm just going to talk you through a brief example here of an agent-based simulation from a fantastic, esteemed academic here. If you're interested, you can purchase the book on Amazon. Last time I checked, it was just a bargain at £69. And I can tell you now that this book has sold over 2 copies in its lifetime, and I don't know if they were counting the one they sent me for free, but nonetheless, it is there. If you don't have £69 burning a hole in your pocket, but you'd still like to read it, there is a link to read the thesis for free here. But then you don't get this wonderful picture, or indeed the picture of a younger looking me on the back that they slightly stretched. So I'm going to talk to you a little bit about my thesis and what I did, and it also combined a little bit of reinforcement learning, which obviously we touched on a little while back towards the end of module 4. So basically my thesis was all centred around trying to build a model of bumblebee foraging behaviour, and basically try and ascertain whether the foraging behaviour of bumblebees, who are known to forage over very large scales, would cause issues if you've got a landscape that contains genetically modified crops and non-genetically modified crops, whether essentially the bees would cross-pollinate GM and non-GM crops, and therefore affect the purity of the non-GM crops. Incidentally, the model predicted that they won't, for numerous reasons, which you can read about. But the model I developed, it was known as Harvest, which for harvesting animals with reinforced values and estimates. Basically, the way it worked, it was set up as an agent-based simulation. So we had bumblebees who were individual agents, and each of those agents was making a decision in an environment, and the environment was essentially a series of patches which represented kind of fields of crops. And each field had a number of flowers within it, and they would essentially choose which field to go to, whether to stay where they are or move somewhere else, and would sample flowers at random within that field. and fill up with nectar. And their goal was to try and fill up with nectar as quickly as possible. And so they were making individual decisions. What do I think is the probability of me finding a flower here that's got nectar in it versus the cost of me moving elsewhere? And what's the movement cost if I do travel to another patch? And they actually used a reinforcement learning rule in order to update their estimates. But it's hard. It was an agent-based simulation. Each of these bees was causing behaving individually, but leading to emergent dynamics. And indeed, one of the emergent dynamics that came out, and indeed is observed in real bumblebee foraging, is that they tend towards what's known as an ideal free distribution, which is basically where, and this happens a lot in ecology, where foraging animals tend to distribute themselves across the landscape such that none of them can really do any better by moving anywhere else. So they kind of self-organise themselves, even though they're all acting individually, so they're all doing well enough. But of course, it's not just bumblebees that we can model. Agent-based simulation can be useful for health as well, which is why we're teaching it. And particularly, I think we've got quite a few people from public health, I think, this year. Hopefully this will be stirring up some ideas in you, because particularly when you're looking at things like public health interventions, agent-based simulation can be really useful, because often the kinds of interventions that you're making and the outcomes from those interventions are basically going to depend on people's behaviour or groups of people's behaviour. So examples might include things like modelling the spread of disease and how you might intervene to try and limit the spread of a disease, modelling the effects of social networks and or interventions on health behaviours, so things like smoking behaviours, alcohol consumption, encouraging healthy lifestyles, healthy diets, all that kind of stuff, where behaviour is at the core of what you're trying to capture, and essentially the sort of main outcome that you're looking for from your sort of what-if analysis, how you might best target your interventions. But really, any system where behaviour is an important part, a core component of what you are trying to capture, is likely going to be right for an agent-based simulation approach. So it could be that you want to model adherence to prescribed medications. In fact, I've done that very thing many years ago, looking at building a model of polypharmacy patients, so patients that have lots of things wrong with them and have to take lots of medications, and most people who are in that position do not take all their medication as prescribed, because, as you might imagine, you get lots of adverse reactions if you're taking lots and lots of medications, and so they tend to drop things and take things sometimes suboptimally clinically, because they want to avoid these adverse events. And so the idea was that we built this model that acted as a proof of concept to try and work out how people were doing that, so that you could essentially feed in different prescription combinations to see whether you could perhaps prescribe something that might be clinically less effective, but if more people would take it, then perhaps that was a better option. You could do things like modelling influences on vaccination uptake, or looking at how decision making might differ under different pressures within an organisation. Anything where you've got behaviour at its core, agent-based simulation can help. Now, it's important. It's very difficult, I think, with agent-based simulation when you start thinking about how you might model this kind of stuff, because your first thought is, we are going to be trying to model behaviours that are probably going to be quite complicated. Where on earth do we start? How do we go about doing that? We may not even fully understand how people are behaving and what they're doing at an individual level, and we possibly won't have the data to parameterize that, even if we could. So we have all these challenges if we're going to try and model behavior in some way. My tip to you, whenever you're designing an agent-based simulation, is to try and think about, first of all, as with any modelling, distill it down to the simplest possible model that will sufficiently answer your question, as we talked about and have continued to talk about all the way through the course. So think about only capturing behaviours that are relevant for the questions you are trying to answer. Most of a lot of you, I'm sure, will go on to do some discrete event simulations for your projects. And I would argue that most of those discrete event simulations will have some sort of behavioural aspect, but in most cases it won't be relevant for what you're asking. If it is, then that's when you need to start considering about agent-based simulation. But if you should only really capture what is relevant, and those behaviours that are relevant and that you do need to capture, you should think about how you simplify these down into simple rules of thumb or simple heuristics. So just to take an example of that and how you might approach that, the harvest model for my PhD, I basically captured the behaviour, the foraging behaviour of bumblebees, but of course I couldn't ask bees how they make their decision. I mean, I did. They didn't give me a sufficient answer. But we do know some things about bee behaviour, and we can use that to try and create rules of thumb. So here's what we do know. We do know that bees are economically motivated. That is, they basically have to continually forage for food, or they die quite swiftly, and they also expend energy when they're travelling. Okay, so that tells us things. We know those things, and that tells us how that might shape behaviour. We also know that bumblebees forage largely independently. So unlike honeybees who have the whole sort of waggle dance thing, bumblebees tend to largely, there is some interaction, but largely they make independent decisions when they're foraging. And we also know that bumblebees trapline, and traplining is basically where you follow the same route through a foraging patch, which a field, for example, here, each time, because we think it's because they know that means if they follow the same route, by the time they get back to the same flower, it'll hopefully will have replenished its nectar. So they're kind of going through in a structured way. And from that we can infer that they probably therefore have some kind of memory, and therefore they're adopting some form of reinforcement learning behaviour. And so those are things we know and can reasonably infer from what we know, and we can use those pieces of knowledge to then try and come up with rules of thumb that we can then try to model. So the rules of thumb that I adopted for the model was, well, each bee is going to try to fill up with nectar as quickly as possible before returning to the nest, and we that's justified because we know that they're economically motivated. So that would seem a sensible behavioural rule. Bees will sample flowers randomly in a chosen patch, and it'll contain either one unit of food, nectar, or no food, and they will retain a perception of the quality of its foraging landscape, which it basically updates via a sort of reinforcement learning algorithm, and it will update that as it finds or doesn't find nectar of its food. And it will also choose the option it thinks to offer the most reward at the lowest cost, because we know that they can't travel for too long, costs them a lot of energy, and it's risky. And so it is reasonable to come up with a rule of thumb that balances gain versus potential risk, so risk versus reward, basically. Let's think about something that's not bee related, though. Let's imagine a fictitious example, or maybe not fictitious. Maybe one of you wants to do a project like this where you are thinking about reconfiguring your waiting room, and you want to basically build a model of the way in which your patients tend to allocate themselves with different seating configurations. And you've observed, you've sat down there and a little clipboard and watched what people do, and you've noticed that older people and those with mobility problems tend to sit nearer the door, that younger people tend to sit towards the back of the room, and that everyone tends to try to sit not next to someone else unless they're older or have mobility problems, or basically they have no choice. And so from that, from those observations, you might say, well, in which case, the rules of thumb that I will capture in my model will be that if the agent is age 60 or over, or they've got mobility problems, then they'll select the nearest empty seat to the door. If they're under 30, then maybe they select the empty seat furthest from the door that's not next to an occupied seat. And then for everyone else, they're going to select an empty seat nearest to the door that isn't next to someone else. But if they can't find anything, they'll just find the nearest empty seat. And so essentially we've created some rules that we can easily code in. We can write these things into code from these observations. We are making assumptions. We don't know that these are the actual behaviours that people are following, but we have derived these kind of rules of thumb from our observations. And indeed, you could sort of part validate your model at the very least by trying to run a little empirical study and seeing if people actually do this kind of thing as you change your different configurations in your model. Indeed, that's exactly what I did for the bee model. I did stand out behind a building on the Exeter campus for a week, with wheeling around some oilseed rape plants and talking to bees and getting strange looks from students who walked past. That happened. But that's the world of agent-based simulation. So the behaviours that you are trying to model. So we've given an example here of bees and patients in the waiting room, but you may also have behaviours where your agents are interacting with each other and or with aspects of the environment in which they live. And again, you should be trying to think about how you might simplify the model and what you capture, so that you're only capturing interactions that are relevant to help you answer your question. So, there might be lots of real interactions that take place in the real world system, but if they don't help you in your model, then do you really want to be modelling them? Because you're just adding in assumptions, you're adding in more possibility to be wrong. So as an example, the waiting room example we just talked about, it's highly likely that people might talk to each other, interact in that way in your real world waiting room, and whether or not they talk to each other might depend on how close they are to each other. So that's something that you could capture, but does it help you answer your question? Well, it might, if people's behaviour is influenced by wanting to sit near other people to talk to them. Because and then you should model it, because you're essentially trying to work out where they're going to sit and how they're going to sit. So if that's going to affect the thing that you're looking at, then you probably do want to capture it. But if not, then it's probably not relevant and you don't need to capture that. We're basically looking, so in that example, we're looking at the emergent population level seating behaviours. So what affects those behaviours? Your agents, as well as interacting with others and with the environment, might also have things that motivate them, or they might have goals they're trying to achieve, just like our bee that they're trying to fill up with nectar as quickly as possible, or they've got various needs. And these motivations and goals, they might influence the behaviours of your agents. If they do, then you probably should look to try to capture them and try to weave them into your behavioural rules sometimes. So, as I say, the fact that bees need to constantly be consuming nectar gives them that rule of they need to sort of fill up as quickly as possible, and that determines their decision making in the model, because they are making decisions about risk versus reward, etc. And sometimes, of course, the needs of your agents might influence their behaviour. So if a certain need hasn't been met, that might alter the way in which they behave, or hasn't been met for a certain amount of time, all of these things can basically influence the way in which they behave. And so then you may even have a little bit more detail where people behave in different ways depending on certain things being true. As an example, maybe in your waiting room, they, individual agents have a need to be kept informed, and if they're waiting too long, they might end up speaking to the receptionist more. If that's relevant for what you're trying to model and for the question you're trying to answer, then that's possibly something you should you should consider modelling. And as well as interactions and goals and motivations, it's possible that your agents may learn. Not all agents will learn. Not all agent-based simulations contain learning. Obviously, my B model did. But if you need to think about whether learning is relevant for your agents. And if they learn and how they learn is up to you as the modeler. Remember, an agent-based simulation, you can do anything you like. So you can come up with your entire, your own entire way of learning. You could chuck in the simplest learning model you can think of, or you can whack in a neural network in there if you want. It's entirely up to you and what you're trying to do. The key thing is to ask yourself, would the behaviours or the interactions of my agents lead to them changing their behaviour over time because of things that they are doing and things that they are learning? And if the answer is yes, then you probably do want to include learning in some way. If that behaviour is going to change over time based on things they do or things that happen to them, then you probably do want to include some form of learning. As I say, that can be as simple or as complex as you like, and just remember that you want it to be as simple as possible to sufficiently capture what you want to answer your question. Okay, any questions so far, Sammy?
No questions in this on this section.
Excellent, cool. Either it's all been very clear or everyone's fallen asleep. Either is entirely possible when I'm teaching. So what we're going to do now is you're going to spend the next probably until about 4. So you've got over an hour. We're running a little ahead of schedule. So next week you're going to see how to build some agent-based simulations in Python using a package called Mesa. But what hopefully you'll see from that is that actually building an agent-based simulation isn't too complex. It's basically, you'll see why I taught you object-oriented coding, because a lot of it's focused around that, with some nice little things that you can use in Mesa to help you do it. But it's fairly straightforward. There's nothing particularly complex. You're essentially making up most of it, so it depends on what you want to do. But I think the real challenge with an agent-based simulation is actually how you go about turning a real-world problem that has behavioural aspects into the design for an agent-based simulation. So that's what I want you to spend time on this afternoon. So you're going to go into groups and you're going to have until 4 o'clock. And I want you to come up with a design for an agent-based simulation for anything you like. Okay, can be absolutely anything. So first of all, I'd recommend you toss around some ideas, have a chat in your groups about what you might want to do, and then decide on one as a group that you're going to turn into a design. I'm going to ask each group when we come back to give a short presentation, no more than 3 minutes, so 2 to 3 minutes. And again, Sammy's going to judge the best. We will get back to you, by the way, about the ones this morning. I haven't forgotten that we're making notes on those as well. And we will be awarding PSG points for the best ideas. So what you should think about when you're putting together your design, think about things like why you want to build the model. What are the questions that you are trying to answer? That's always has to be the first question you ask whenever you're doing any modelling, not just agent-based simulation. But if this is an agent-based simulation, then you think about, well, what is the emergent behaviour that you are looking to analyse? What agents are you going to have in your simulation? What do your agents represent? Maybe you'll have more than one type of agent. You don't just have to have one. You can have different types of agent. What behaviours will your agent or agents have? Will your agents learn? They don't have to, but is that relevant to what you want? And if so, what will they learn and how will they learn? What will your environment represent? Will your agents interact with each other and or the environment? And if so, how will they do that? What will that look like? Will your agents have specific motivations or goals or needs, and how will they be represented? Also think about, as you're going through this, think about how you're translating this into behavioural rules of thumb. So try to come up with simple rules of thumb that can capture the real world behaviours that you're trying to capture. That's a really important skill when you're doing agent based simulation. And also, as you're thinking about all this, think about what you see as the kind of primary reasons for choosing to do whatever you're trying to do as an agent-based simulation, other than Dan's told us to spend an hour designing an agent-based simulation. But why, for that particular thing you've come up with, why do you think that's a better approach than one of the other modelling approaches that we've covered, for example? Okay, so I'll open up the breakout rooms now. Go and have a chat about some ideas, and then start to design what your agent-based simulation will look like. Think about those behaviours, think about those rules of thumb, the interactions, the agents, all that kind of stuff. So I look forward to hearing what you come up with. I'll be rattling around and listening in, and we will come back at 4 o'clock. So don't forget to have. It doesn't have to be anything more than a slide if you want, or something you can talk to for 2 or 3 minutes. The key thing that we'll be looking for is just for you to describe an interesting idea and how you thought about how that might turn into an agent-based simulation. Okay, let me open up breakout rooms. Okay, everyone, welcome back. It's time to see what you managed to come up with. Some really interesting ideas as I was floating around the room. So some really interesting stuff I think we're going to see now. Just before we move into that, I'm just going to hand over to Sammy, who's we've been talking about the point allocations and for the exercises this morning. Sammy, do you want to tell us how you've distributed your points?
Hi everyone. Yep. So great work as always. Couldn't really separate a lot of you in exercise one. So we're giving 20 points to Pokey, TIA, Zylog, and Paula. 20 points to all of you. Very well done. And in exercise two, your insight maker models, that we are going to give 20 to Denise and TIA, 30 to Arm, and 40 to Paula. So very well done, everyone. Really nice stuff.
Fantastic. Thank you, Sammy. Yeah, brilliant work. As Sammy said, lots of really interesting models that came out of that. So brilliant to see. So let's see what agent-based simulation designs you've come up with. So I tell you what, let's go in reverse order today. So we're going to start with Zylog first of all. So someone Zylog wants to talk us through your design for an agent-based simulation.
I'm happy to talk us through if no one else is going to. So I'll just share my screen. So what we've done is we have. Sorry, can you see my screen?
Not at the moment, no.
Oh no. Let me try again.
Oh, something's coming up now. Yep, there you go.
Perfect. So what we've done is we've used agent-based simulation to model a music concert. So this is our presentation. So while building the model is we want to create this to understand how people distribute themselves at concerts. So you can understand like where to put toilets, exits, bars, it's like front of the stage and open space. It's also important in terms of security, like safety of people going to the concert. I think there's images from the Who concert where unfortunately the crowd wasn't well managed. So it's important for safety as well. So in our simulation, the agents are the concert attendees, and we have various types of agents of different behaviours. So we have the thrill seekers, whose goal is to get to the front. So they want to be crowd surfing, barrier hopping. We have the chill seekers, who are the people who want space, want to relax and enjoy the concert, maybe dance around a bit. And we have the escape artists, who want to leave the concert as soon as possible when it ends, to ensure they get the last train home and or in bed for an early night. So the environment obviously is the concert venue. We know that concert venues can have different shapes and configurations. So we can have a catwalk, a circular stage or a straight stage. There's different types and numbers of exits, and there's different locations and numbers of amenities. So bars, merchandise stands, etc. Then we have the interactions, which is the agents moving around the concert venue, around the 2D floor space. Can be 3D if you've got some crowd surfing, but we didn't bring that into this part. And the reasons needing to move are accessing the amenities based on need or based on the behaviour. So the needs are hydration, bladder, how many numbers of trips to the toilets they need, which is linked to hydration, energy, and the need for merch. So we chose agent-based simulation because it can reproduce the behaviour of concert attendees, and it can be used to provide an explanation for the collective behaviour at concerts. These images are actually from papers that have been published in the past, like modelling similar concert venues, concert attendances, and disasters at concerts. So yeah, that's our presentation. Thank you.
Fantastic, thank you very much. Really, really impressive. Really liked that. Lots of creative thinking, and what a great use of agent-based simulation. And really thought through the how that was going to work and how your what your agents represented and their sort of behaviours and the different types of agents. So yeah, really nice work. Fantastic, really creative stuff. Brilliant, thank you. Okay, so next up we've got TIA, please.
That's me. Bear with me. I'm just.
Yeah, no worries.
Yeah. Can you?
Yep, that's come through.
Fantastic. So we also went to the concert venue, but from a different take, the need to have some food when you're at the concert and the complexities of this. And we also had a segue via puns and AI-generated illustrations. So bear with me as we enter the world of Glastonbury. And how to define our wonderful project in one sentence. What better person to tell us than ChatGTP, who told us that in this simulation, every agent creates their own unique experience in a world of endless possibilities. What's our agent? Well, it's this gentleman who appears to have three hands, one of which is completely disconnected from his body. And this person has to decide what they want to buy food-wise. So the buyer is the agent, and we thought about some of the things that might affect his behavior, or their behavior, sorry. So whether they're cash sensitive, time sensitive, choice sensitive, how hungry they are, if they need a coffee or not, because not all stands will send you coffee. What's their affiliation to the music? Are they a muso? In which case, will they run to see a band and preference to feed themselves? And then we thought we might have an action state somewhere in there. We had some distractors that we didn't quite know where to place, but we thought somehow should be modeled. So whether they need to go to the toilet and whether that was influenced by the waiting time to go to the toilet and what type of band was playing. And in the case of the AI generated picture, the band seems to be some sort of Bhangra rock fusion band. So would they rush to see some Bhangra rock fusion? And also some variables that are sort of external from this, such as whether it's raining or not, or because you'll see, to answer one of the questions, what's the minimum number of customers you need for the stands? And then there's the food options, and then we let it rip there. I think, Dan, you'll see we have some food options. So these are the environment really that they can access. They've got Cornish, I can't really do it, Cornish pasties, there you go, which has a moderate price, but no coffee. Then Bun Times, which has a sort of a high waiting time, but moderate price and no coffee. And Cheapest Chips, that has a low waiting time and low prices and coffee. And Lobster Fun, which sells lobster rolls that are both expensive, but have coffee available and the waiting time is low. So that was the environment. Why did we want to have agent-based simulation? Well, we thought about some of the other models. Discrete event simulation wouldn't account for those personal choices and an evolving environment. Same thing with system dynamics, and also the flow would be people, and that didn't seem to fit. And also we thought that the ABS might allow us to have some emergent behavior, so we could see how the pattern and the reorganizations between the stands happen. We gave you a couple of example rules. So for example, you might say that if they're highly choice sensitive, then they'll only queue for their preferred stand, but things might be a bit different if they're medium choice sensitive, and then it would decline other parameters. And the sort of questions we wanted to answer is what happens if we've got an extra stand? Can you sustain it? And how can a stand increase its number of customers? And an unanswered question will remain, will Oasis be playing?
Brilliant. No, thank you very much. Again, a really, really creative. I like the way you've taken a similar thing, but a completely different tack with this. And again, really well thought out how you've considered the way in which the agents will interact with the environment and the different behavioural rules of thumb. I think that's really good. I mean, you're only a couple steps away, I think, from a proper conceptual model that you could put into an agent-based simulation there. So yeah, really nice use of agent-based simulation, and 10 out of 10 for the Cornish accent and the wonderful puns, and not to mention, of course, the as always unusual AI artwork. So brilliant! Thank you very much. Fantastic. Okay, so that's TIA. So Sid, you're up next.
Oh yeah, sorry, just finding the right screen to share.
Yeah, no worries.
Cool. Hopefully that's the right screen.
Yeah, that looks okay.
Okay, perfect. Okay, so yeah, our idea of this model was looking at how to sustain recovery from alcoholism. So specifically, once someone has gone to rehab, has detoxed from alcohol, how can they stay sober? So the sort of questions we were looking at answering is, what are the things that influence long-term recovery from addiction to alcohol? What would be the causes of relapse? What can we put in place to support long-term recovery? So are the things we can see in this model that that tell us how we could prevent relapse for people. And then in terms of emergent behavior, we had lots of discussions about this. I think we thought that the main thing was someone's proclivity to drink. That was kind of the key emergent behavior. But then we were also wondering whether we would be able to pick up patterns that might be linked to relapse or sustained recovery. Certain kind of, if there is like some sort of positive feedback loop there. So our environment, I think we decided, was just anywhere that isn't, the hospital, basically, anywhere outside of rehab. So people's social environment, where they work, their family, their interactions with healthcare services. So the agents specifically are people who've gone through recovery. The behaviors of the agents would be having a job. What is their job? Also, do they regularly attend their job? That sort of thing. Going to the pub, that's a big thing. For recovering alcoholics, is that something that these agents are doing? What are their social interactions like? Are they, do they have a rich social life? Are they attending therapy? Are they taking a camprosate, which is a drug that can support recovery? Do our agents learn? So we were thinking, would they be learning coping mechanisms? So would they, through attending therapy, would they learn coping mechanisms? Also, if they were to relapse and re-recover, maybe they would learn from that experience and learn how to reduce that happening in the future. And in terms of interactions, our agents would interact with each other. So they might encourage or discourage each other from drinking. So you might have like a sponsor. And also they interact with the environment. So they might be going to the pub. They might, be speaking to a therapist, to a doctor, to work. I think we're struggling a little bit to look at interaction / behaviors. And then in terms of motivations, we thought that the overall goal would probably be to stay sober, but then a lot of people would have different motivations for that. So is it to keep a job? Is it to maintain the relationships? Is it something else? And then also we thought emotions might play into this. So it might both affect how someone is likely to recover from alcoholism, but it might also be an outcome of staying recovered. And we thought agent-based simulation, because it's a lot about complexity of behaviors. So yeah, as it's a big human behavior problem. I'll stop talking now.
Brilliant. Thank you very much. I know, really, really interesting. I really like that, and I think that's a really nice example, I think, of how agent-based simulation can be used, where you've got this sort of really complex emergent behavior and a lot of potential for interactions. I think particularly, things like the social interactions and whether they're sort of choosing to do things in terms of their self-help, so attending therapy and taking medication, etc. That could then in turn influence not only what happens to them, but also to others in the system as well. So I think that would make a really interesting agent-based simulation, actually, and a really nice way to approach that. So yeah, brilliant. Well done. Thank you very much. Okay, so next up, we've got Pokey.
Okay, that's me. I'll just great, is that showing?
Yeah, that's come through.
Cool. So yeah, our team looked at a fire evacuation in a hospital setting. So this was to look at the question, how does the building layout and individual behaviour impact success during a fire evacuation? So in this, we had as our agents the fire itself. So in terms of how far it can spread, whether it's been contained by fire doors, whether there's been any extinguishers used. And then we had a kind of parent class of people where we'd have subclasses of patients, staff and visitors. And then these would have varying levels of morbidity, kind of priority to leave. So either whether they'd focus on their own evacuation or whether for staff they would be aiding other patients, and then kind of knowledge of the hospital. So you would expect staff to like know where places are more so than the patients and the visitors. We explored some of the behaviours, kind of exiting by the closest known exit, and then staff assisting with patients, particularly mobile patients, and then the motivations for wanting to evacuate the building, prioritising patients leaving, and directing patients to the exit. So in terms of the environment, this would be a hospital. So kind of looking at a floor plan of a hospital, what fire escape exits there are, the signage for fire evacuation, and fire doors. We decided in terms of the agents learning during the simulation, there would be a kind of global knowledge network of what wards had already been evacuated and how much and where the fire has spread. And why we thought agent-based simulation would be good is because of this modelling an environment and this crowd behaviour. And that's us.
Brilliant, thank you. Again, really interesting idea. I really like that, and it's what I particularly liked as well about yours is that you really considered having the fire as a separate agent. I think that's a really nice idea that you sort of brought in a second agent and considered the fire in that way. So I really like that. And what a great use for agent-based simulation in that sort of again, agent-based simulation is often used for things like crowd control. And then putting it in an emergency situation like that, and observing, how different interventions will play out with all these sort of interacting behaviours of the people that are trying to evacuate, as well as the hazard that they are trying to evacuate from. So yeah, really interesting. I really like that. Thank you very much. Okay, so Paula next.
Oh, that's us. Share screen. Hopefully it comes up with the right one and nothing else.
Looks like it.
Yeah, all right. So we went a slightly duller route in terms of our question and for the ABS. So we went down with a potential project question that I'm hopeful it might be among potentially one of the first ABS models of the HSMA program, but we shall see. But our question was to deal with, can we model the progression of COPD and namely look at the impact of being on certain prescribed medications, as well as potentially other interventions, all with the aim of ultimately understanding and reducing emergency presentations for these patients. So, but that fully realizing that that potentially has a few too many things within its scope and needs a little bit trimming down. But nonetheless, in terms of agents, so that naturally would be patients with COPD. We've marked it on the slide with a asterisk, just because there's possible needs to consider kind of complicated comorbidities and the influences of that. So potentially limiting the study down to patients with only COPD or select other comorbidities that have been deemed appropriate to include. In terms of studies, behaviours, we've jotted down ideas in terms of the engagement with primary care, namely the interaction with or having annual reviews, inhaler technique and self-management plans done and reviewed on an annual basis, with the medication adherence as another behaviour to look into. In terms of learning aspects, there would be a potential for looking into the perception of a patient's condition or state of health. So things like this could be seen as influencing the likelihood of a person potentially taking breaks or not adhering to certain medication or engaging with their practice as much. In terms of rattling on down the list, the environment would be the sub-ICB district that I or others may work in, and the communities within. And in terms of interactions, there's possibly more interactions to do with the environment, namely the engagement with primary care and services such as pulmonary rehabilitation. And in terms of motivations, that would be ultimately the aspect of health maintenance and minimizing disruptions. But like others, the rationale really for ABS was namely that in comparison to, say, DES, the main influences to whether or not a patient interacts with services is up to their own wants and needs, not simply about the availability.
Brilliant. No, thank you very much. I absolutely think that would make a great HSMA project, actually. I think that's really well thought out. I think I like as well that you've considered in terms of the learning. I think that's a really interesting aspect where you're thinking about how the behaviours of these patients are likely to adjust as their health deteriorates or as it potentially improves as they you always got a sort of reinforcing effect where they're doing things that will help them or vice versa. So I really like that, and I think that's that would make a really nice agent-based simulation. I think that's a really nice approach for it, and is actually not dissimilar to the very first project I ever did with the Pencourt team. When I first joined, when it was just me, Tom, and Martin were the Pencourt team, and that was using agent-based simulation for diabetic retinopathy progression. So looking at progression of a condition and then sort of the interventions, etc. I think that's a really nice use of that simulation method. So yeah, really, really good. Thank you very much. Fantastic. Okay, so that's Paula. So Motorola next, please.
Hi.
Hello.
Is that all
Yeah.
okay? Showing okay? Thank you. So we looked at vaccination agent-based simulation for our team. So in terms of the overall question that we're trying to answer, looking at what factors affect people's uptake of vaccination and the overarching emergent behavior around whether people will take the vaccine. The agents that we have within this simulation as healthcare users in England, the behaviours, either accepting vaccination or choosing not accepting vaccination. Around agents learning, we had quite a big discussion around this, but learning to accept the vaccination if the prevalence of COVID would increase, alongside learning to not take up the vaccination, such as aspects like misinformation spread or concern around health status. The environment itself we've done as England, so it's a bit of a broad stroke overall, but we've done that as an overall look at the environment and the agents within England. In terms of interaction, we've listed these out as separate aspects. So peer pressure alongside misinformation or disinformation, but those can be combined factors. So that was around interactions with each other, interactions with the environments as accessibility to vaccination sites, and the environment also as media, news, or the internet as parts of that environment also, which was also an interesting one to think about in terms of how that is captured within the model. So the agent motivations, goals and needs, vaccine hesitancy, the availability of services, a motivation and a goal to reduce the likelihood of COVID or long COVID or effects from that, such as mortality, the accessibility, again, to vaccination sites, and then other health risk factors, such as comorbidities, and then mobility as well comes into the proximity side also. Primary reasons represents the behaviour of individuals within that population and able to explore and draw up motivations, further thoughts and ponderings. So the question that we had was for vaccine uptake, but around vaccine hesitancy, we included misinformation. Would we need more? There's other agents such as vaccine services, etc. How would we include those in the model? Sorry, I went a bit over there.
No, that's okay. No worries. No, really, really interesting. I think that's a really interesting use of agent-based simulation. I could see that being particularly impactful, actually, to explore. Because I think you're right. There's a lot of behavioural aspects that come into a vaccination, and we've had people that have before tried to do sort of forecasting around vaccination uptake, but actually I think there's so much in terms of the behavioural aspects that influencing, and particularly interactions with other people, and as you say, with media and sites on the internet, and all of that kind of stuff. And you could even weave in a lot of social network analysis stuff in there as well. So I think this would be really ripe for exploring lots of different actions. So I think definitely this would be a great agent-based simulation. So thank you very much indeed.
Thank you.
Okay, so that's Motorella. So Denise up next.
Okay, that'll be me. Let's see if I can just share my screen.
Oh, I can see myself.
Can you see that okay?
Yeah, that's come through.
Okay, right. So we've not done something quite as rock and roll as some, but hopefully it'll be useful and interesting. So we had some ideas between us, and the one we settled on was an idea that I'd been kicking around as a potential project idea. And we took advantage of Dan dropping into our room just to run it by him to see if it was a good approach. And it came from the sort of recent events of, if anyone recalls that sort of recent failure with the cybersecurity software that took a lot of GPs basically out of circulation. And it for us, operating 111 services, it caused a big spike in demand as patients were redirected towards alternative services. So why did we want to build an ABS model for this? And it was really around trying to see how the different parts of the system interact with each other, as well as with the patients as the agents. So within here, certainly the patients themselves are agents, but also GP surgeries, 111, and hospital A&Es would potentially act as agents with their own agendas and motivations within that. The behaviours we're trying to model are things like, why did patients choose one part of the system over another at a given point? and do those patients potentially learn to navigate systems? Well, certainly, at least anecdotally, yes, it would suggest that they do. I'm sure we've all experienced that at some point. So the environment that we're trying to build is really, at this point, a kind of simplified local NHS system. We thought we could maybe even just at this point look at one GP, its interaction with A&E and sort of one local A&E and with the 111 service, but potentially at a project level, we might scale this to cover a whole sort of county or an area, perhaps. The patients will probably less interact with each other, but more interact with the services, but also the services will interact with each other according to their motivations. So, for instance, the patients are obviously interested in the treatment, getting the right treatment at the right time, and that might vary according to their condition at the time, and that might worsen, for instance. And for the other parts of the system, so grouping, GPs, ones and A&E together, they've got their own performance stats to meet, but also care quality as well. But it's interesting to see how those different stats overlap. So, for instance, taking the example of, say, like a wait time for an ambulance outside a hospital, that doesn't necessarily concern the hospital per se, or the GP or 111, but it is intrinsically linked with how the others behave and how the system all interacts. So why agent-based simulation? It was really to give us that zoomed out sort of helicopter view of the system as a whole, as opposed to what we sort of, or certainly what I see at the moment, which is just sort of those individual parts. So to be able to link them all together through this seems like a good thing.
Brilliant. No, thank you very much. Again, yeah, really interesting idea. I think a really creative use of agent-based simulation to look at something like that. And I think that again, so much behavioural influence within a system like that, and something like that happening that leads to massive pressures for other people and other organisations within the system that are so drawn from what individuals and the individual organisations are doing in terms of their behaviours and how they're acting under pressure. I think there's a whole really interesting aspect to that. So yeah, fantastic. Thank you. Okay, so last few, you've got Armop next.
Hello everyone, I'll just share my screen. So hopefully you should be able to see that fantastic artwork.
We can indeed.
Excellent. So we decided we were going to ask a very important question about what would happen if you basically played The Sims on an island, but instead of humans, they were just all drunk monkeys. And obviously there's also a subtle tone here about the evils of AI art, as you can see going on in the background here. I cannot unsee that ever. So basically, as a background, in real life, not in our simulation, some monkeys were brought to the island of St. Kitts, and they basically developed a taste for alcohol. So they would raid bars and pubs and all that sort of stuff for drinks. And each monkey has a different sort of liking for alcohol. Some won't drink at all, some will drink a bit, some will go completely crazy and drink everything, kind of just exactly like humans do. And it also says down here, interestingly, that the very heavy drinking monkeys make good leaders. So I don't know why they chucked that in at the end anyway, but we've worked that into our simulation as well. So why are we doing this? Apart from so I can show off some other evil AI art, as you can see down here. So we're two things, sort of. Obviously, you can compare the habits these monkeys have to humans, but it's in a much more controlled situation. And also just because I'm slightly worried that drunk monkeys might take over the world. So I just wanted to make sure that wouldn't happen with this simulation. So the agents, obviously, we have the monkeys, and much like humans, they will probably drink differently based on their age, their background, genes, even monkey peer pressure, and all of that as well. So we kind of went through and just listed down all the different aspects of it. So here we've got like the behaviors, interactions, and motivations. So monkeys would compete with humans and other monkeys for booze. That's sort of interactions there. You've got like why you would want to be a drunk monkey, because apparently they're the most successful leaders, so you could have more power as a drunk monkey if you're one who likes drinking a lot. The other quite interesting thing is that monkeys are quite spiteful, so they would actively go out their way to limit access to alcohol for other monkeys as well. So I thought that might make quite an interesting model. Oh, and there's a picture there. Cool. So the environment is a island with a number of different bars and pubs, each with different risk, rewards, and proximities. You know, some may be very well guarded, some may not be, some may be near other monkeys, and some may be miles away, so it's too far to get there. But once you get there, you get a very high reward. And you've got adversaries, whatever. Hostile monkeys or humans are the bar owners. So why did we do this, or why do we use agent-based simulation for this? So as we said earlier, not all monkeys are the same, so let's see what impact those differences had, and also because then you can input the learning and reinforcement behavior, so like how and where to steal, and they can adapt their motivation based on what they're stealing. But yeah, that's where we got with that.
I don't think I would have ever in a million years thought of designing an agent-based simulation to assess drunk monkeys on an island. I think that's incredibly creative, and I like the way you tied that into something potentially really useful as well. So yeah, fantastic, really really interesting and really well thought out how you've created your agents and the interactions there. Brilliant, thank you. What great ideas we're seeing. This is brilliant. So just two left. Antic up next.
Hello.
Hello.
The screen.
Yep, that's come through.
So we had pretty much similar one that we had with Denise. We also looked into the agent-based simulation to looking at what influences where the patient might go for their treatments. For our agents, we had our patients as our main characters in the environment of the city where we have multiple care providers, naming from A&E, GP practice, pharmacy, and 111. We looked through their behaviors in terms of trying to understand what they might want to do, where they would go, and would they have potentially some kind of a capacity in terms of how long they might want to wait in a queue if the area is too full. The learned behaviors we look to give our patients over time is learn the past experiences with a care provider itself. For example, if they had a bad experience in the A&E by waiting for too long and having a very noisy environment alongside with the long wait time, they might not enjoy that and might want to choose something else if they get the choice. They're also looking at their own severity of illness and sustainability of the care provider. For example, if it's not so severe, they might not want to go anywhere. Or if it's very severe, they might want to just choose whatever is available, regardless if it's an A&E, GP, pharmacy, or 111, and they would go to length of going through every single one of them. Or availability in terms of open times. One with the GP practice, they would like try to get that one very quickly if possible. Otherwise, they might just go to A&E as a result. So our agents will interact with all the environments in terms of, we could also think these environmental locations as their individual agents, as the organizations, and what they might want to do if they have an influx in demand. For example, we can choose if there's certain day availability in terms of open or not, or depending on situations such as winter time, there might be a high influx of specific type of demand. We then would look at the agent decisions in terms of what would influence their actions, but in our case, it's mainly the patients, so they would not directly influence each other's actions aside from increasing the queue time on a specific environment or the destination where they would like to go to. We then look through potential agent motives, goals, and needs. So for example, what level of motivation for care, if they want the best care available for their condition, or they want to just solve it as quickly as possible and go to the nearest environment or care provider where they can have severity of their illness, for example, if I may have a heart attack or just or a fever, depending on if I can lie in at home and have paracetamol or something similar, or how long it would take care to go there, depending on the times, capacity available for appointment, previous expensive provider. And why we chose the agent-based simulation is to look at the motivations of care providers' needs in relation to the population deprivation and quality of care treatment versus ease of access.
Brilliant, thank you. Again, really, really interesting. I think again would make a great actual agent-based simulation. I think that's it's a really interesting area where you've got kind of patient choice dynamics within health and social care systems, and there is a lot of interplay, I think, between those different factors. I think really interesting to explore that. So yeah, brilliant. Thank you. Really well thought out. Okay, so last up, we've got Agnes. Apologies, we're slightly overrun, but nearly there. So Agnes, you're next stop.
That's me. Hold on. Can you see my slide?
Yes, we can. Yeah.
Okay, so what we chose to make an agent-based simulation for is simulating restaurant choice in a city center. So, ooh, can you still see my screen?
No, it's just disappeared.
Okay,
Oh, it's
can I
back.
get 20 seconds back? No. Basically, yeah, so the emergent behavior we wanted to explore is, given the current set of restaurants on our street, how does this affect people's motivations for where to eat? And does how much would a change in setup affect this behavior? So the agents in this simulation are hungry people attending the restaurants. The behaviors of the people are, well, I guess they're the traits of each agent that affect how they act are whether they're willing to experiment with food choices, what their preferred cuisine is, their budgets, how willing they are to walk a longer distance, how hungry they are, which affects how willing they are to walk longer distances. And once they run through the simulation and come back around, whether or not they previously had a nice experience at that restaurant. The rules of thumb associated with these behaviors are, whether someone is more likely to eat at their preferred cuisine. No, the rules of, sorry, let me correct that. So the rules of thumb that affect behavior are the fact that people are more likely to eat at their preferred cuisine, go to a restaurant that's within their budgets, their hunger levels. So, someone that's more hungry will be less likely to walk a longer distance. And familiarity with the restaurant. If someone's more familiar with a restaurant, the rule of thumb is that they are very likely to return back. The learning or the stored memory, let's say, of each agent when they're attending these restaurants are, so yeah, what needs to be stored is like remembering the restaurant they went to previously and keeping a record of whether or not they enjoyed it. The environment is our street full of restaurants, which will change, which we can change to sort of explore the relationship between the setup and where people are motivated to eat. And then the interaction between the agents and these restaurants are, looking at the menu, reviewing the distance and all of that information before making a choice, even though that's not direct interaction with the restaurant. Yeah, it's like one step behind. When they eventually go to the restaurant, there's sort of like a record made of how the experience was and their hunger levels change. So agents obviously want to choose a restaurant that meets their requirements, food they like within their budget. And we chose DES because the agents have individual choice and act independently. And DES is a bit too one by one discrete.
Brilliant, thank you very much. That again, really, really interesting and creative application for agent-based simulation. And again, I could see that as an agent-based simulation. I mean, in many ways, that's a lot of the early agent-based simulation games, things like Theme Park, etc., were based around a lot of concepts that you're covering there, setting up different sort of food stalls and restaurants, and that you would look at what the people would have different preferences, and depending on what they did, would lead to different dynamics occurring across the park. So yeah, really interesting. I think yeah, again, a nice, really creative use. As with all of these, some fantastic creative ideas that we've seen, and I hope to see at least some of these turn into projects. Now, I think, Sammy, would I be right in saying you'll need a bit of time to think about how to allocate points here?
Yes, that would be appreciated. There's an awful lot of, I've made a lot of notes, and yeah, would like to do them justice, but yeah, really impressed. Some very creative ideas, and you've really thought about a lot. So yeah, great to see.
Fantastic. No, thank you, Sammy. So we'll get back to you probably tomorrow with the point allocations for that. But yeah, fantastic, really fantastic presentations this afternoon. So thank you for that and for staying on a little bit over. Next week, we will look at how you can build these agent-based simulations using the Python package Mesa, and you'll see hopefully that it's actually not too bad, and it'll give you a nice opportunity to practice your object-oriented programming skills. In fact, I would argue, and I mentioned this earlier in the course, that if you're still a little bit unclear about object-oriented programming, and it still seems a bit weird in your head, agent-based simulation will help you understand object-oriented programming, because it's almost the perfect demonstration of why object-oriented programming is so useful. So all that to come next week. So thank you again for today. I hope you've enjoyed it. We've covered lots of different things today. Next week, back to Python. We'll send out the instructions tomorrow. There will be an environment that you will need to install, which would include Mesa, but it shouldn't. It's fairly straightforward. Shouldn't cause too many issues. But I look forward to seeing you all next week. See you, everyone. Bye bye.